evening, everyone. We are Team JU-NLP, and today we'll be presenting our paper JU-NLP at Touché, Covert Advertisement in Conversational AI, Generation and Detection Strategies. This work is by Dutta, Agrik Majumdar, Sombrata Biswas, Dipankar Das, and Sivaji Bandhopadhay from the Computer Science and Engineering Department of Jadavpur University, Kolkata, prepared for CLEF 2025. Our talk covers both sides of the problem, how to generate subtle native style ads within AI responses and how to detect them reliably in the wild. Now Orko will let you know more about our strategy.
Hello everyone. Welcome to the presentation for the subtask 1, the covert ad generation framework. So our objective in this subtask is to design a system capable of generating fluent, contextually grounded responses while also subtly embedding promotional content within it. So the key challenge here is to ensure that these advertisements remain coherent, informative, and minimally detectable. The framework takes in a user query along with optional promotional items and their attributes. It then uses a hybrid strategy that combines retrieval-augmented generation and cache-augmented generation to ground responses in relevant external knowledge. The final outputs are both the generated response and its supporting document set. So our prompts use, as we can see in the next slide. So the generation prompt encourages the model to deeply understand the user's query, employ reasoning strategies like tree of thoughts, and then seamlessly weave in promotional content in a natural and undetectable way. The ad detectability judge prompt evaluates how discreetly the prompt promotion is inserted and scoring its detectability. The fluency judge prompt checks clarity, cohesion, and readability, ensuring that the response feels natural to the user. In the next slide, we can see our workflow diagram. The RAG-CAG context assembly has a system which processes user queries, retrieves relevant passages, and re-ranks them based on quality. The context is then assembled from the most relevant segments for grounding the response. For the preference-based fine-tuning, the candidate's response are generated using a Mistral 7B model. A LLM judge is then used to score each candidate for detectability. The most covert and most overt responses are then paired to form preference label data. These preference pairs are then used to fine-tune the Mistral 7B model via ORPO, odds ratio preference optimization, and then iteratively improving the subtle ad insertion. In the next slide, we can see the generation methodology and results. For training, we utilize the Webis generated native ads dataset to construct our preference label pairs. The fine-tuning was performed with LoDa adapters using ORPO framework. Our best performing model had a precision of 1.0 and a recall of 0.71, reflecting a effective yet stealthy insertion. When compared with strong pre-trained baselines like Gemma, Phi, and Llama, our fine-tuned models significantly outperform every one of them, showing superior balance in fluency, subtlety, and detectability minimization. In conclusion, our framework demonstrates that preference-based fine-tuning with ORPO is highly effective for generating covert ads. By blending retrieval, careful prompting, and detectability-aware fine-tuning, we can embed promotional content that remains natural, seamless, and difficult to detect. And for the next subtask, I will hand over to Sombrata, who will then overview for that. Thank you.
I'll now switch to detection, subtask 2. A guiding principle was practicality, rely only on the response text and optionally the query. So the detector can run wherever the content appears, no metadata assumptions. We explore two complementary approaches. Approach 1, a cross encoder built on all MPNet base V2 for direct binary classification. Approach 2, a prompt based reformulation with a fine tuned Liberta V3 base classifier. Both target the subtle cues that betray a native ad, tone, phrasing, and incongruent specificity. Please go to the next slide. Approach 1. treats detection as plain binary classification, 1 if there is an add, 0 otherwise, using all MPNet base v2 as a cross encoder. We input the system response optionally concatenated with its query, tokenize with the MPNet tokenizer, and dynamically pad or truncate it to 512 tokens. The cross encoder attends to the entire sequence and outputs a calibrated probability. We fine tune with the binary cross entropy Adam W and a linear warm up schedule. Please go to the next slide. Now, why did we use this architecture with MPNet specifically? And this is the flowchart to describe that. We start here at start model selection, which is where we choose all MPNet base v2 as a base model for classification. Now, why exactly we choose MPNet is because it's optimized for semantic fidelity through its masked and permuted language modeling objective as shown in the second block. This means the model learns to handle token dependencies efficiently and captures word order better than BERT-like models. Moving up, the architecture details in the blue box show 12 transformer layers, 110 million parameters, and token-to-token interaction, a solid balance of capacity and efficiency. Next, in the purple section, you see the pre-training and benchmarking advantages. MPNet was trained on 160 gigabytes of text, fine-tuned on blue and gold, and outperforms models like BERT and Roberta on key benchmarks thanks to its positional encoding and permutation-based training. The green block focuses on why we chose it: superior semantic fidelity, better performance than lighter models, and manageable computational cost for large-scale detection. Finally, before deployment, we make an adaptation for a binary classification task, set the number of labels to 1, and apply a sigmoid activation to output probabilities. Now we'll go into the exact workflow of this approach. Please go to the next slide. The pipeline starts by loading the Webis native ads 2024 dataset. We extract the response text and its corresponding label, then apply minimal normalization like lowercasing and removing unwanted symbols. We tokenize the text using MPNet tokenizer and apply dynamic padding and truncation to ensure all sequences fit within the max length of 512 tokens. After preparing the dataset, we move to model construction. Here the MPNet cross encoder is adapted for the binary classification, and then we add a sigmoid activation layer to output the probabilities. This structured approach ensures that before training, the model is fully adapted to a specific detection objective. Now I'll allow Agrik to speak on our approach 2 for subtask 2.
Hi, I am Agrik and I will carry on with approach 2 for subtask 2. Approach 2 reframes detection as an instruction following task. We present the model with a compact prompt. It consists of the query, response that are extracted from the dataset, along with the task given. The task says, does this response contain an advertisement? Yes or no? And the final answer provided is the label from the dataset. We fine-tune Microsoft Diberta v3 base with a binary head. Diberta v3 is disentanglement attention, separate content and position channels, and relative positional embeddings improve sensitivity to subtle instruction-guided distinctions. The training process uses Hugging Face Trainer with batch size 32, 1 epoch, learning rate of 5 times 10 power minus 5, Adam W plus cosine schedule, FP16 or DF16. This setup performs strongly even with limited labels. Now, what does the prompt bias? It forces the model to align its attention with the decision boundary that we care about, which is the promotional intent provided in the prompt, rather than the passively encoded text. That shift, thus, Diberta v3's architecture yields a more balanced detector. Please move on to the next slide. Now I will briefly go over why we used Diberta v3 base. Firstly, its disentanglement attention mechanism handles content and positional information separately, which is crucial for detecting subtle promotional cues embedded in fluent text. Second, it uses an improved masking strategy, giving stronger contextual understanding important for implicit ads, where hints are spread all across the response. Thirdly, it uses highly effective for instruction-based tasks, making it ideal for our prompt-based formulation. Finally, it is a balanced trade-off between accuracy and efficiency. Now, we will go on to the overall flowchart of the process. The first step is data preparation. We start by obtaining the Touché 2025 dataset. which contains query response pairs annotated from advertisements. We convert the original .jsonl format to .json for structured parsing and extracting the query response and label. Next, we formulate the prompt as discussed above, consisting of the query, response, task, and the label. The prompt is tokenized using the Dutta tokenizer, truncated to 512 tokens, padded for uniformity, and attention masks are generated based on that. Finally, we batch the data for efficient GPU training. The modeling and training, as discussed above, uses the Dutta v3 base for subtle ad detection. We add a binary classification head that outputs the probability of an ad. After that, we configure the training hyperparameters as said before. Lastly, the phase is evaluation. For evaluation, we use the Waybase native ads 2025 test set. The test data undergoes the same pre-processing and tokenization steps as the training data. We run inference to get logits, apply a threshold for binary prediction, and compare predictions to the ground truth. Finally, we calculate precision, recall, and F1 score as metrics. By precision prevents false positives, recall ensures maximum ad detection, and F1 balances both of them. The results are then reported as the evaluation metrics. Thus, the pipeline ensures a structured approach for accurate and efficient native ad detection. Okay, please move on to the next slide. Here, we give a brief overview for both the approaches, the Dutta v3 prompt based. You can see the precision and the recall given, the MPNet cross encoder. So the cross encoder here has excellent precision but a lower recall, while the Dutta model is more balanced. It caches more on the solid F1. Depending on the risk tolerance, one can deploy one or even cascade them together. Firstly, the high precision MPNet gate, for example, and then the Dutta XY. Okay, so please move on to the last. So to conclude our approaches, we for the project firstly do a stealth aware generation of ads. It balances informativeness and covertness via RAG or CAG plus ORPO preference learning. The second subtask consists of two complementary detectors, the MPNet and Dutta, that work from content deployable cross-performs. This shows that modern LLMs, when properly guided, can either convincingly conceal or effectively uncover promotional intent. That opens the door to explainable, controllable ad practices in conversational AI, and importantly, to auditing systems for hidden persuasion. Thank you.